It is my great pleasure to introduce one of our co-PIs and co-organizers and co-friend, not co-friend, actual friend. It's like you're not in the category of, okay, so Christelle Vincent, who could not be here in person, but she is here online with us to tell us about quantum computing and post-quantum cryptography. Hi, Christelle.
Hi. Yes. Um, I'm really happy to be able to be here in at least some capacity. I'm really sad to not be there in my usual capacity. So usually I give like a whole week of like, well, not the 4 days, but it feels like a week of mini courses, and I stay for the research conference. So it's a little sad, but it's also a little not sad because the reason I'm not here is that I'm on sabbatical and that we decided to come to Tahiti in French Polynesia. So I'm not saying that only to brag about my awesome life, but also to warn y'all that it's 5:30 a.m. here. That's how much I wanted to speak to you. I woke up at 4:30 a.m. But I may misspeak because it is not my usual morning time. So I want to start the talk. If there we go. It was like just a little TLDR. Kind of the whole story of the talk is that quantum computers are coming, maybe, and maybe soon. And I'll say more about that. Why the maybe? And that if they come and if they are developed in the way we hope, that will have effects on all of our lives, hopefully positive ones, but also negative. Um, so I want to start just with like a little history of quantum computing. I think it's a good way to kind of introduce the subject. So in the early 80s, as far as I could find, Feynman was the first person to propose this idea. They were doing research in simulating quantum phenomena on, what I will call classical computers, what are just computers now. Um, and there were like kind of too many moving parts, too many things to simulate, and they were not really able to do it. And in a talk in 81 and then in a published paper the following year, Feynman suggested that if the computer used quantum phenomena, it might be able to simulate quantum phenomena. And just this talk, as far as I know, and the resulting paper is kind of what sparked the study of like theoretical quantum computing in the early 80s. People started developing, the math that I will talk about briefly, and how any of this might be possible. In about 1998, right, the late 90s, so almost 20 years later, companies finally started coming out with actual quantum computers. Like that's the experimental era of quantum computers. So I always like to have at least one picture, just so like what is the quantum computer. So this is the D-Wave 2X chip. It was actually released in 2015, so a quite late experimental quantum computer. And if you kind of keep track of like qubit numbers that I give you during the talk, this chip had 2048 qubits. Half of them were turned on when you bought the chip, but not all of them worked. And kind of more interestingly, the number of qubits that worked on the chip were like dependent on the physical chip, like which individual chip was yours. Each of them was like a beautiful, unique individual, which is still the case today in terms of qubit, which is really interesting. And to give you an idea, right, if you're not like really a computer person, I say, okay, this chip had 2000 qubits, and you're like, maybe that's a lot, maybe that's not a lot. The laptop I'm giving this talk on has 68 billion bits of RAM. Like not the storage, but like the actual like rapid access memory. Oh, sorry, my window's open and the neighbor's cat just came in. So yeah, so like 2000 to 68 billion. Um, then for a while we were in this like experimental era of quantum computing, and then in the late 2010s, 2016, the mid 2010s, we entered the current era of quantum computing, which is the NISQ era. So you can like throw that word around if you want, which means noisy intermediate scale quantum computing era. So I will talk a lot more about the noisy part of it. For now, I'll leave that a little vague. And the intermediate scale is the number of qubits that the machine has. So it's kind of like, if you buy a computer that has like 2 gigs of RAM, 4 gigs of RAM, 8 gigs of RAM, and now I'm sure that it's like 16 or whatever. Right, so that's kind of what we mean, like by how many qubits a computer has. And so current quantum computers have, on the order of like 1,000 or 10,000 physical qubits in them. And the hope, right, the future, like why we've been working since the early 80s on doing all this, is to have what they call utility scale quantum computers. So, like, not intermediate scale, right, but a scale, a size of quantum computer that's large enough to do something, to be useful. With the goal of obtaining quantum advantage. And quantum advantage is just this simple concept of like doing something with a quantum computer that you can't do with a classical computer. And that's kind of interesting because we've had quantum advantage and we've lost quantum advantage. So in 2019, Google, with their Sycamore chip, claimed quantum advantage. They solved like a really hard random circuit sampling problem in 200 seconds. And at the time, they claimed that it would take the fastest current supercomputer like 10,000 years to solve the same problem. I mean, that was like kind of immediately disputed. Google is a company, they are trying to sell their stuff. Was it just to repeat, that was 2019. And in 2022, a team of the Chinese Academy of Science solved the same problem in hours on a like super cluster of computer, like using thousands of classical computers in parallel. So, it was like something no one could do on a classical computer. They did it with a quantum computer. And then when we kind of like really put our mind to it, and worked on it for like several years, then they were able to do it on a classical computer. And some possible applications of quantum computers, like we don't have them, so it's hard to know exactly what we'll do. But in terms of like real world problems and benefits that we might get, for me, strangely, well, maybe because I'm a gardener, the most interesting one is to simulate bacteria to produce ammonia. So interestingly, ammonia is crucial to farming. The development of industrial processes to generate ammonia is like linked to us as a species moving out of food scarcity, like being able to have like a very small number of people make food for everybody in the world rather than like everybody farming their own land and making just enough for themselves, because ammonia is a fertilizer for plants. But producing ammonia the way we do it now and the way we've done it for 200 years is like really bad for the environment. Estimates say that like 1 to 2% of all carbon emissions in the world come from producing ammonia, and 80% of industrially produced ammonia is for farming. So like a relatively large amount of our carbon budget goes into making ammonia. But if you garden like me, maybe you know that you can plant legumes in your soil to help with the like soil. I mean, I didn't know the details until I started studying quantum computing, but legumes have these rhizomes and there's bacteria that live in there, and these bacteria make ammonia, and they don't contribute to global warming, and we don't know how to do it. And so one area of research is people studying these bacteria and attempting to understand how they do it so that we can have greener processes to make ammonia. So we can still have food, but not the global warming that comes with it. Another thing a quantum computer could do is modeling proteins to discover new drugs, right? So chemistry, like lots of molecules, lots of atoms, lots of stuff that could happen. Trying to kind of search through the space of what molecules might be useful as a relevant computing problem. And quantum computers could help us get better drugs, better cancer treatments, better anything treatments. And maybe finally predicting the weather, right? The weather is, again, like a really complex system with a lot of variables, and quantum computers could potentially keep better track of all these variables and give us better predictions. Saving lives. Like if you know better where a tornado is, when it's coming and where it's coming, you can evacuate. You can, well, maybe not tornadoes, maybe hurricanes. You can prepare, you can evacuate, etc. So these are all the kind of like shiny things we hope that quantum computers might do in the future. Now, how is that possible, right? I think you should be very skeptical of someone coming and being like, this magic box will magically solve all of our problems. So I'll give you like a little idea of like how that might be possible. So just to really back up, in classical computing, current computing, the kind of basic object is the bit, and a bit takes value 0 or 1, right? That's it. That's what it does. In quantum computing, the basic object is the qubit. I've already used that word, so it's for quantum bit. And a qubit in mathematics looks like this. So this bar with the wrangle, this symbol is called a cat in quantum computing. And I'll just start by introducing you to alpha and beta. Alpha and beta are two complex numbers, such that the magnitude of alpha squared plus the magnitude of beta squared is equal to 1. And then these cats, 0 and 1, are these column vectors. Okay, so the 0 cat is just a column vector 1, 0, and the 1 cat is just a column vector 0, 1. And so really, this maybe looks like forbidding and like, oh my gosh, what could a qubit be, right? But if you do like distributivity and linear combination, right, a qubit mathematically really is just a vector of length 1 in C2, right, with 2 complex coordinates. And so I hope that this kind of gestures at why a quantum computer might be able to tackle more complex problems. In classical computing, the basic object can take 2 values. And in quantum computing, the basic object can take an uncountable number of values. So there's kind of a lot more information in 1 qubit than there is in 1 bit. And that's kind of how you can do computations a lot faster, is by using this extra space in the unit of information. Is that quite as good as all that? So if I gave you a bit, whatever that means, or whatever it is that you're holding in your hand, if I give you a bit, you would know its value, right? You would know if it's 0 or 1. Essentially, giving you a bit is giving you a value 0 or 1. If I give you a qubit, whatever that means, whatever a qubit is in the physical world, it has an alpha and a beta, right? The main information of it is these 2 coordinates in the vector, but you can't see them. You can't access them directly. What we can do with qubits is measure them, quantum measurement. And again, mathematically, formally, quantum measurement behaves the following way. So you pick an orthonormal basis of C2, right? So a basis of C2, 2 linearly independent vectors that span C2, and it has to be orthonormal. So both vectors have to have length 1, and they have to be perpendicular to each other. And you smush your qubit in that basis, right? You do measurement, you do the act of quantum measurement, and the outcome of it is that you'll observe either the first vector in the basis with probability equal to the magnitude squared of the projection of your vector on that basis vector, or you'll observe the second basis vector with probability equal to the magnitude of the second, the projection of your qubit on the second basis vector squared. So the simplest example of measurement is to use, what we call the 0-1 basis for measurement. So these cats that we already know. So 1, 0, and 0, 1, that's an orthonormal basis for C2. So it's a valid measurement basis. And if we have a qubit in this state, right? This is just a qubit because I didn't specify alpha and beta, but if it's in the state, then we'll observe the first basis vector. So we'll observe 0 with probability the magnitude of alpha squared, and we'll observe 1 with the probability the magnitude of beta squared. And so you might have heard, if you've heard about quantum computing or stuff, the Schrodinger's cat, like these kinds of things that do transpire. A qubit, right, rather than being 0 or 1, is kind of 0 and 1 with certain probabilities, right? You have a certain probability of observing 0 and a certain probability of observing 1 when you measure the qubit. And these probabilities can hold information. That's the idea of quantum computing, is to find a way to make these probabilities mean something. So that's the end of the introduction to quantum computing. Before I move on to post-quantum cryptography, I just want to make a little pitch, because it is rare that I have a room full of talented upcoming mathematicians in front of me. So quantum computing needs mathematicians, number theorists, all kinds of mathematicians, because qubits are very fragile. So now we're getting to that noisy part of the noisy intermediate scale quantum era, or NISQ era. So if you have a qubit, whatever that means, I'm holding it in my hand, it has an alpha and a beta. Sometimes the sun sends a photon and the photon hits the qubit and the qubit changes value. The alpha and the beta can change. If I try to manipulate this qubit, right, apply gates, so just like in classical computing, right, you don't just have bits and you're like, ooh, my bits, right? You like act on your bits to do computation. So there's gates in quantum computing too. And you act on your qubit to compute things. So sometimes you'll apply a gate on your qubit and the outcome is like not at all what it should be because of noise. So that's what I mean by qubits are very fragile. Like in theory, there's a vector, there's a matrix, a gate will be a matrix, and you just, do multiplication, you get some answer, but in practice, actual physical qubits are much harder to deal with than that. And so one way in which mathematicians can help, and so physicists are working on this and getting like better physical qubits. Engineers are working on this and getting, better materials, cooler materials, better transmission of information, better shielding from radiation, all that, right? And apart from this kind of like physical work on making the qubits better, like more resilient, hold their values better, there's a lot of work to do in math to just deal with the qubits we have and make them better kind of theoretically. So one thing that we can do when we have a noisy transmission between, people is redundancy to mitigate errors. So suppose that I wanted to send you just 0 or 1, right? Like just like one bit, I want to tell you 0 or 1, yes or no, I'm coming tonight. But say that there's a 10% chance, right, that in communication, my answer will be flipped, right? So if I say yes, there's a 10% chance you'll actually receive no, and then you won't expect me and there won't be any food for me and it will be very sad. So one way I can do it is like send yes, 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 right? Or no, no, no. And then if there's a 10% chance and it's independent that each of my responses will get flipped, then if you get like yes, yes, no, you might think like, okay, she means yes, right? Just that no got flipped. So with a repetition, right, you can decode the answer that I sent. And so this is a situation, right? This like little repetition code where I use 3 physical bits to encode 1 logical bit, right? So like this is a string that could contain 8 answers, like yes, no, maybe, only if so and so is not there, only if you make the good pizza, and so on. But no, right? There's not 8 answers that I'm trying to send. There's only 2 answers, 0 or 1, and I'm using 3 physical bits to send my answer. And so that's very much what they do in quantum computing right now. They do quantum error correcting. So they'll have many qubits, physical qubits, that together can be interpreted to be the state of one, like, better logical qubit. So just almost a year and a half ago now, the paper came out in January 2025, but was already on the archive in 24. Google's Willow chip, the successor to the Sycamore chip that I talked about before, used 105 physical qubits to encode 1 logical qubit. And this was the first time in all of the world that adding qubits reduced the error rate. So going back to this repetition code, if there's a 50-50 chance that my answer will be flipped, right? And then saying yes more or saying no more won't help, right? Because if I say like yes, 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 but 50% of them get flipped, you'll get a string that's about 50% yeses, 50% nos, and like you don't know the answer. And even if I send you more yeses, right, if they get flipped with odds like 50%, then you don't get any information, even if I keep talking to you. So until 2025, 2024, right, all qubits were so crappy, and all decoding, right? There's not just the repetition code. The repetition code is actually like not our best code. There's better mathematics there. All of our qubits and all of our quantum error correcting codes were not good enough. That anytime you add qubits, you just added more noise rather than adding clarity. So for a year now, we've had qubits that are physically good enough and error correcting that's mathematically good enough and fast enough to get qubits, physical qubits, such that the more you have, the better you're holding the value of the qubit. And to put things in context, right, this Willow chip had 2 logical qubits. So, like 210 physical qubits that they could keep together. A different place where mathematicians are needed, right? So mathematicians are very much working on these codes, like making better codes, making better decoding algorithms. Another place where mathematicians can work, I talked about gates, applying gates to qubits. So there are matrices. So physically, because of just how life is, the kinds of matrices you can apply to a qubit are unitary matrices. Those are matrices such that the inverse of the matrix is the conjugate transpose. So you just take the normal transpose of the matrix and then the complex conjugate of each entry. And some gates are worse than others for noise. So there's certain operations that you can do that like you get the right answer. And there's some operations that you do and like you don't, right? Just like physically, that one is kind of like really hard to realize in real life. And so there's a lot of math work being done, like that's group theory, to optimize circuits to minimize the use of bad gates. And so anyway, I think those problems are really interesting personally. And so anyway, right, quantum computers are amazing. Everybody rejoices. This is going to be great. Or does everyone rejoice? Right? So we haven't said that, but this is kind of like Alvaro's unofficial fifth mini course lecture. You've been working all week on hard problems in cryptography, the discrete log problem. I believe Alvaro talked also about RSA, so factoring integers, right? So there's definitely people like me who actually love hard problems and don't want them to be solved. So now I want to talk about kind of the flip side of quantum computers. Like they're good, right? They're good. The benefits to humanity far outweigh their impact on cryptography, but it's something cryptographers have to think about. So just to kind of maybe repeat something that Alvaro said or present it differently. I looked at Alvaro's slides, but didn't like listen to the lectures. So I don't know what he said. I only know what he wrote. So algorithms in cryptography have all sorts of functionality. So my understanding is that you talked about Diffie-Hellman key exchange, elliptic curve Diffie-Hellman, right? So that functionality is for two people to end up with a shared secret number that they know and no one else knows. So that's a functionality. You've talked about Al-Gamal encryption, right? So that is sending a secret message to someone. So that's like one functionality. Al-Gamal signature. So that is, authenticating the fact that the message really came from you and not someone else, right? That's a different functionality. So that's what I mean, right? There's different algorithms that kind of do different things. But all of them are controlled both by the specific algorithm and a parameter called a key. So that's what I want to talk about just a little bit. There's two main kinds of cryptography in terms of key, right? So secret or symmetric key cryptography and public or asymmetric key cryptography. So secret is the same as symmetric and public is the same as asymmetric. And everything that Alvaro talked about is all public key or asymmetric key cryptography. Well, when he did the history and he talked about the Vignere cipher, that's a secret key cryptography. And the Enigma machine, that's secret key cryptography. So I guess not everything he talked about, but everything he kind of really talked about is public key crypto. Just to give you another example of secret or symmetric key cryptography, the Caesar cipher. So if you want to send someone a message, one thing you can do if you're in kindergarten, right, is write your message in English or whatever language you speak in kindergarten, and then replace each letter by some previous letter in the alphabet. So maybe you decide 2 and you want to send someone the letter D, then instead of sending D, you send them B because that's 2 letters before in the alphabet. And so the choice of K, right, 2 instead of 4, 5, 10, that's the key for this instance of the Caesar cipher. And in this case, when your friend gets, B as a message from you, then they use the same key 2 to decrypt the message and get the letter B, which is actually what you wanted to send them, right? So that's why we call it symmetric key cryptography, is because you use the same key to encrypt as to decrypt. Like I kind of said, what Alvaro talked about in class is mostly public or asymmetric key crypto. So Al-Gamal encryption is an example. PKC is public key cryptography. Cryptographers love their acronyms. And so if you fix a prime P, an elliptic curve over the prime field FP, and a generator big P for the group of rational points of your curve, right, then a person, their secret key would be some scalar K that they choose and keep secret. And their public key would be the point P plus P plus P plus P plus P K time. So in this case, right, this public key is the encryption key and this secret key is the decryption key. So this is asymmetric cryptography. There's 2 keys. The encryption and decryption key are different. And so the difference, right, is that just to like really harp on it, in symmetric key use the same key, and therefore the key has to be secret. So that's why it's called secret key crypto. And in asymmetric key crypto, there's two keys. And because of that, you can make the encryption key public because it doesn't allow you to decrypt. You need a whole different number or object or thing to decrypt. So that's why one can be made public. So that's the explanation of those words. And the reason why this is even possible, right, to have a secret key and a public key, and you can make one of them public and you can keep the other one secret, is because there's math operations that are easy to do and hard to undo. So for the rest of the talk, I'll be talking mostly about RSA. So integer multiplication and factorization, right? It's easy to multiply and it's hard to factor. What I mean by that, right? I don't mean hard like, I'm asking you to compute log 2 and you're like, I don't know how to compute log 2. Computing log 2 is actually easy by this definition. So a problem is hard if the best algorithm we have to solve it is an exponential time or sub-exponential time algorithm. So that means that the amount of time it takes to solve the problem grows exponentially in the size of the problem. So, to factor a number, to factor like a 3-digit number is pretty fast. A 4-digit number is a little longer, 5, 4, 6, 7, and so on, right? The way the number of steps grows is sub-exponential, is the technical term for it. A problem is easy if we have an algorithm to solve it in polynomial time. So that's kind of like exponential, but with polynomial swapped in, right? So the amount of time to solve the problem grows polynomially in the size of the problem. So multiplication, right? If you have 2 3-digit numbers and you have to multiply them together, well, you do like the ones with the ones, the ones with the 10, the ones with the hundreds, and then the tens with the ones, and the tens with the tens, and the tens with the hundreds, and so it's like n squared operations to do n squared, and like then there's the adding the carries and all that, but that's linear. So it's about n squared operations. Actually, you can multiply 2 n-digit numbers in n log n steps. N squared is like more than you need, but the point is that that's a polynomial function. So to show you that in a picture, I made this graph on Desmos. This green, not green, that's red. That's the color red. So this first curve here that's red, for people who are not colorblind, is exponential, just 2 to the x. This purple curve here next to it, that's the actual complexity of factoring a number, or like close to, there's an O of 1 in the complexity, so I just chose a constant. But that's how much time it takes to factor a number using the general number field sieve. So I don't know like what Alvaro said exactly about factoring, but the general number field sieve is the fastest algorithm we have to factor really big numbers, so numbers that have at least 100 digits. So you see, so this one is exponential and this one is sub-exponential. So it's not quite as big, right? I mean, like it's quite smaller than exponential, but it's like close enough to exponential. And this green curve here, that's x squared. So that's the cost of
Christelle?
multiplication. Yeah.
Hi, Christelle. Just a comment. So I
Oh, yeah.
talked during my lectures, I talked about the Pollard's P-1 algorithm and then Lindström's factoring algorithm with elliptic curves.
Oh,
Do you
okay.
know what the complexity is of those two compared to the number sieve, the number field sieve?
Probably like right underneath here. They're both sub-exponential too. Yeah.
Okay.
So very similar. Probably you would not be able to tell the difference on here. Every factoring algorithm worth teaching in a cryptography class is sub-exponential. So I'm pretty confident in that answer, even though I've never looked them up. And so, right, the security of RSA relies on the distance between this green curve and this purple curve, right? I can multiply two 60, wait, that's 80, two 80-bit numbers. I mean, in real life, they would be much bigger, but that's what I got on my graph, right? And it takes me like this amount of time. That gives you a 160-bit number. And for you to factor it, right? Like, I mean, we cannot even see on this picture how much time it would take. So that's what I said, right? So this graph kind of tells you mathematically what I mean by it's easy to multiply but hard to factor. And and therefore RSA is safe until we have quantum computers. So now the two parts of the talk hit each other. So I do want to say, like, over time, problems have been getting like quote unquote easier just because we've got better computers, right? So we've been upgrading cryptographic parameters to keep up with technology. When RSA was first deployed in the real world, people used RSA moduli that were like 500 bits or like 1,000 bits for like super extra security. And now 3,000 or 4,000 bits are recommended. That's just because computers have gotten that much faster. So to quantify this, I pulled some numbers from the internet. This RSA 100 is a modulus with 100 digits, not bits. In 91, it took a team of people like a few days to factor. And then in 2012, like it was down to 72 minutes. I also pulled numbers for RSA 110 just to show you, right? A number that's just 10% longer, goes from like 72 hours to 4 hours to factor. So this is the same team that factored both RSA 100 and RSA 110. So, like certainly we have to update parameters to keep up with technology, but with Shor's algorithm, right, on a quantum computer, it's just like completely different, right? In 94, Shor showed that if you had like a large enough quantum computer, right, a utility scale quantum computer, you could factor a number with n digits and n cubed steps, which is like very much below sub-exponential. So I've redone the graph. So that's the same graph before, with this first curve here being exponential growth, this second one here being sub-exponential growth, and the green curve being x squared, so the cost of multiplication. And now this curve here is x cubed. So that's the cost of factoring with Shor's algorithm. So I mean, like, okay, at first, right, it's actually worse to use Shor's algorithm than to use any sub-exponential method. But pretty soon the cubic is lower, and I mean, this is like up to 80,000 and 180 if you have more space on top, right? So here I've only changed the y-axis to go up to 10 to the 7. So below here, I don't even know if you can see the green curve, right, which is x squared. It's like essentially constant compared to the other functions here. That's x cubed, so that's the cost of factoring with Shor's algorithm. And this one here is sub-exponential growth, so this cost of factoring with our best classical algorithms. So you start to really see, right, how much better Shor's algorithm is than what we can do on a classical computer. And then I zoomed out even more, right? So this is going all the way to 1,800. Like, we're not even in cryptographic sizes yet, right? Cryptographic sizes now are like 3,000 bits. But you see, how the distance between classical factoring and Shor's algorithm on a quantum computer to factor is a lot faster. It's still slower than multiplying. There's a little advantage here that you can exploit, right? You can still multiply like to like really, 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 really big number. And even with a quantum computer, it takes a long time to factor. And someone did the calculations. If you look up PQ RSA, so post quantum RSA, like just Google post quantum RSA, and you'll find a paper that computes it. But it's like the size of the modulus to attain like modern cryptographic security is like in the terabytes. So for this gap to get big is like too far in the world. And so the development of quantum computers, right? When quantum computers get good enough to actually run Shor's algorithm that threatens, and here I wrote most of our public key cryptography protocols. And by most, I mean like 99%. Almost all of the cryptography we use now is based on either integer factoring or the discrete log problem, and specifically the discrete log problem on elliptic curves. I've never really heard of anything else being used. Like that's why I say most, because it's like maybe I've not heard of something, but basically quantum computers will just raise the field. And kind of just like another way to illustrate how quantum computers are changing the story, right? So in 2018, 2020, let me check, I wrote it down. Yeah, in 2018, a team factored RSA 230, so a number with 230 bits, right? Like this is like 200 digits. Like what we're using is 3,000 digits. Like it's much bigger, right? But they estimated that it took them 10 to the 23 operations. To put this number in context, the age of the universe in seconds is like 4 times 10 to the 17, right? This is more than the age of the universe in seconds. Current estimates on like how much time it would take or how many operations it would take for a quantum computer using Shor's algorithm to factor the same number is 3 million operations. 3 million seconds is like 30 days, right? So I mean, if you transfer like operations to seconds, like this top one is like 10,000 times the age of the universe, and this bottom one is like 30 days. Like that's just like what Shor's algorithm does to cryptography. Now, of course, right? Like how near is the threat? Like definitely we got a few more years, right? So I just pulled this paper last night that was released in March of 2026. So like the very, very latest estimates where they used Shor's algorithm to, well, they didn't because they don't have a quantum computer, but they estimated the resources it would take to factor RSA 2048, so modulus with 2048 bits, or break the discrete log problem on an elliptic curve over a prime field where the prime p has 256 bits. And they estimated that the number of logical qubits, right? Remember the difference between like logical and physical qubits. These qubits are so noisy that you actually need like more physical qubits to encode logical qubits. So it's on the order of 10,000. They estimate the number of physical qubits that would be needed to realize this number of logical qubits using the kind of quantum error correcting codes we have now, if like we don't improve on correcting errors on the math side. And they estimated that, if we had such a big computer that had this many physical qubits, that could realize this many logical qubits, it would take about 97 days to factor RSA 2048 and 10 days to break ECC 256. So, I mean, these are impressive and these are not safe at all. But like we need to get to a place where we have this many physical qubits and we're still like very much in the low thousand, like, Quantinuum this year in 2026 had a chip with 94 logical qubits. So, like on the logical qubit side, we're definitely on the like 100 qubits. So far from like 10,000. So we don't know when it's coming, but we're still preparing. So 10 years ago, NIST began to standardize post-quantum crypto. So I think that Alvaro talked about that a little bit. But basically, for elliptic curve discrete log, what NIST does is publish, a prime, a curve over that prime field that it has like checked its irrational points have prime order, and then a generator for that group of points. And they're like, hey, if you want to use, elliptic curve cryptography, like here's a good curve candidate for you. So this is both like a service, because then companies can just use it without like everybody researching their own elliptic curves. But it's also used in the law, right? So privacy laws like HIPAA or FERPA, when they say like you have to keep information private, they actually say you have to keep information like at least as private as, this elliptic curve that NIST has published on their website. Oh, it looks like, okay, the internet, everybody's waking up here. So, they started to do this work of publishing standards. And I want to just like do like a quick thing. There's post-quantum crypto, which is what I'm talking about. And there's quantum crypto, which is what I'm not talking about. And funnily, post-quantum crypto is before quantum crypto. So post-quantum crypto is done on classical computers. Like I'd be willing to bet $50, I didn't check, that Zoom is using both classical and post-quantum crypto to encrypt this call, the data that we're transmitting to each other. So it's happening now. It's happening on these computers. I don't have a special computer. Quantum crypto will be in the far future where everybody has a quantum machine at home and can use the quantum machine to encrypt and decrypt data. So post-quantum is when there's like one adversary or maybe more, right? But at least one adversary that has a quantum computer to attack you. And quantum crypto is when everybody has a quantum computer and uses quantum phenomena to encrypt and decrypt or sign or whatever. And so finally, in the last 13 minutes, I'm going to tell you a little bit about the math of post-quantum crypto. So there are right now 5 main problems, right? Hard problems that are proposed for post-quantum cryptography. So to replace integer factorization and the discrete log problem. So the first one is code-based cryptography. The idea, if you know about coding theory, is kind of simple, right? Encoding data allows you to recover it even if there's a little bit of noise. So to send a secret message, you would encode it and add a little bit of noise and send that to the person. And this person is the only person who knows how to decode the message and get back what you were trying to send. So it's like repetition code, right? But where no one knows to take the majority. So that's code-based cryptography. The next hard problem is like multivariate cryptography. So this one makes signature algorithms. And here the signature is like a large system of quadratic equations, usually over F2. So, x1 squared plus x2 squared plus x4 squared plus x6 squared, and x1 squared plus x3 squared plus, quadratic equations, like many variables. And then to sign a message, you give a vector of constants and a solution to that equation. So kind of like to the equation that's given by those constants. So here, kind of the public key is this system of equations, but without the constant. And the private key is that you're the only person that can solve this system of quadratic equations every time. The next one is hash-based cryptography, which is actually like not mathematical at all. And I cannot tell you anything about it. Cryptographic hashes are just like, it feels like just mixing numbers in a big vat of soup. And so you just hash things, and there's Merkle trees, if you want to Google something about it. Then there's lattice-based cryptography, which is like very number theoretic. And I'm actually doing like kind of okay on time, so maybe I'll be able to say something. But if not, I will post my slides on the Zulip, and you'll be able to read the slides where I kind of talk about lattice-based cryptography. Like they're pretty readable on their own. So if you're interested. And then the last family of problems is supersingular elliptic curve isogeny, which Sarah Arpin, I believe, will talk about this weekend in her talk at the research conference. So I won't say anything about that. But both Sarah and I work here in supersingular elliptic curve isogeny. So these are like the 5 families of problems that we're considering right now. So you might think like, okay, well, looks like you're all set. But there's a lot of issues with post-quantum cryptography. So the main one of them is how like heavy it is. In this first row here, I've given the parameters for elliptic curve Diffie-Hellman, like as it's used right now on the internet. So the public key size, right, the point Q that you put out in the world is like 64 bytes. A ciphertext, right? So an encoded point is also 64 bytes. Generating the key, so from your scalar K to get the point Q is very fast. Encrypting data, decrypting is like all like very fast. I mean, this is not really encrypting, this is encapsulation and decapsulation, but this is what Alice and Bob do, right? All like beautiful, fast. These public keys and ciphertext like fit in little internet packets like really well. The 4 algorithms below are all post-quantum algorithms. So the first one, Kyber 512, is lattice-based. It's currently deployed. So if Zoom is using post-quantum crypto to encrypt this message, to encrypt this transmission, it is almost certainly using Kyber. I mean, maybe 512, maybe 700. Like, I don't know the exact security level they're targeting, but whatever. Okay, so this one is deployed and standardized by NIST. Okay, but you see, it's pretty fast in doing the operations, but the public key size and ciphertext are just so big, right, compared to elliptic curves. The next 3, those are all code-based. So McLeese is like the oldest code-based cryptography, super trusted, has been studied, like it's maybe 50 years old now. So we have a lot of trust, but like, look at that public key size. Like, I mean, we cannot use this on the internet, like not for going on Amazon and buying things. People throw their computers out the window. HQC that stands for Hamming quasi-cyclic, and Bike, those are a little bit more reasonable. Right now, NIST, just last year in March 2025, has decided to standardize HQC over Bike. Even though Bike has like slightly better performance than HQC, NIST has a little bit more confidence in the safety of HQC. So we'll have a second encryption, decryption, or what they call a CAM, key encapsulation mechanism, standardized. So right now, the NIST has standardized a lattice-based algorithm for encryption, decryption, and they're in the process of standardizing a code-based algorithm for encryption and decryption. On the signature side, they've standardized kind of like the sibling of Kyber 512. It's like called like dilithium because, we're nerds. Which is also lattice-based, and they've also standardized already a hash-based signature scheme, and they're working on standardizing another lattice-based signature scheme. So right now, the things that are actually being deployed are code-based, lattice-based, hash-based post-quantum crypto. There's still very much work being done on supersingular isogeny and multivariate cryptography. It's just the big exemplars of those were broken in the last 10 years. So people are trying to come up with new things. So Certainly, you're right. One issue is that the algorithms that are chosen are based on few problems, like lattice-based, code-based, that are pretty new. Um, there's a competition now in progress to get more signatures. So there's definitely still work being done on post-quantum crypto, like mathematical, like theoretical work being done on post-quantum crypto. And we need mathematicians to develop more hard problems, like add to the list of five, right? Like a sixth or seventh. Because what if someone comes up with a quantum algorithm to break lattice-based crypto, or a classical algorithm to break, multivariate crypto? So we need to just come up with new ideas, more algorithm based, either on old ideas or new ideas, and also just people working to break them. So the big exemplar of supersingular isogeny cryptography, Psych, was broken in 2022 using math from the 80s. So it's not that we didn't know the math that would break it all along. Psych was proposed, in the 2010s, so that math was already done. But it's just we needed enough people aware of Psych and knowing math that the idea that ended up breaking Psych would come up, right? So we're very, very much not all set for post-quantum crypto, and we're very, very much chasing elliptic curve Diffie-Hellman, like something with like really small key sizes and really quick encryption and decryption. And we don't have that yet. We don't have like anything that's as good. Um, I think that I'll actually maybe end here rather than try to go through. Like, I have a few more slides on learning with errors, which is a lattice-based problem. But like I said, they're pretty readable, so I'll put them online. And so if anybody is like, okay, lattice-based crypto, this Kyber is being deployed. What is it? What's going on? It's kind of interesting and weird. Um, and I'll just let you read that if you want, and just stop here with 3 minutes to spare.